I have to correct something I said in class that was incorrect. I apologize for it. This has to do with transforms. It has to do with really the phase of second current. This is the main thing for the current of secondary. I want to go through this and make sure it's crystal clear about this. Also in your quizzes, only magnitude counted. The angle didn't matter. So that, what I said in class did not affect that. So I want to make sure everybody follows me on this. This is for transforms. Now in the book, for transforms. They're going to have I1 coming in here, plus to minus V1. They're going to have plus to minus V2 here. Then there's going to be some Z load here. Now, there's also going to be something like this. Follow? N is really the number of the ratio of turns on secondary to primary. So if you think about N1 and then divide it into N2, that's really what N is. Just think of it that way. Because it's normally N1 and 2. So if you look at the voltage, it's V1 over V2 is proportional to N1 over N2. That's true. Absolutely. But N2 over N1 is really 1 over N. On the board, I put down N by mistake. You follow me on this one? It's always the ratio of the terms. V1 proportional to N1, V2 proportional to N2. But really, they always make this just 1, so only thing you're looking at is N2. You follow me, class? That's the way you think of this. Now, that's true. That's absolute. The next thing they do is this. Now this is Dave Irwin saying he does it this way. I'm not sure if everybody does this. This is for transformers, not for mutually coupled circuits where we had the M and the J omega L and the JM. But here, they're going to label this current out of the secondary in this direction as I2. Right. Now for that, they also say that now I2 over I1, or really, let me do it this way, to be consistent. I1 over I2 will be equal to simply N. And really what I'm saying, I do it this way. I don't even really pay attention to that. I always say, when I look at this, if I go from 1 to 2, I know voltage is greater here by a factor of 2 than it is here. If it's 1 to 5, voltage is greater here than it is here by a factor of 5. That's how I look at transformers. Now if it was 2 to 1, I know this voltage would be 1/2 this voltage. This is how I always do it. Do y'all understand this, class? I'm trying to show you the way yeah.
So, in coupled circuits, we don't have the current going into the terminal. For transformers, it can be going out but still be positive.
For mutual circuits, the current goes into the dots on both of them, all right? For transformers, unfortunately, this is his choosing. If the current was going in here, then this ratio would be negative. Do you follow me on that? They put a negative. I don't want to do that, and he didn't either. He left it positive. He just said this is going to be a positive ratio, this is positive. And this too, by the way, is really, since this is really going to be N2 over N1 here. And I'm really trying not to focus too much on, I'm just focusing on those equations. I really like doing it this way. I mean, I know current's going to come out of that dot now, all right? Now, just hear me. The way you can actually figure this out without that, if you have a voltage here, V2, you can figure the current there, right? Just take V2 by Z, right? Now, you can figure the current here too by just get the reflected impedance from that side over here. The reflected impedance has no polarity. Are you with me? Once you have the reflected impedance on this side, you can replace that transformer with the reflected impedance and solve it, then you'd get I1. Are you with me, class? So you wouldn't even have to really bother with the current ratios. Follow me in this class? I want to do just a simple problem completely and make sure everybody can see this. So there's no mess up. So, nothing complicated. I'm just going to do 624 again, but this time with everything right, and I'll show you the way you sort of can't go wrong. If that makes sense to you. I'll try to. If we're going to do this problem, this is going to be 624 part 2. Random markers. All right, so 6.24 again, and for this one, you're going to have a voltage of plus to minus 24 at an angle of 60 degrees volts, and then you're going to have 4 plus J6 here. 4 J6 here. Get some of the markers. Then you're going to have this. And after this, be out here, and they're calling this I2. They're calling this I1. I'm going to show you a trick on this one. All right. Now with transforms, this is the one thing I want you to remember. If you take a transformer and you flip the thing like this, both sides, it doesn't change the input-output characteristics. Do you understand that? Transformers transform AC voltage and current. If you take the dotted terminals and flip them, it doesn't change the problem at all. Did you all hear me? All right. It doesn't matter if both dots are on the bottom or both dots on the top. This is a gift. You got that, class? It doesn't matter. So you can do this. You can just go ahead and take those dots and put them here. Now, why did I do that? Because I want my voltage right here. I want to make that V1 and that V2. It will not change a thing. You got that, class? Both dots are on the top or both dots on the bottom. Now, if there's a dot here and a dot down here, when you flip them, they still are going to be on opposite sides. You all see what I'm saying? You get me on this one? Remember, these are AC circuits. That's the reason you can do this. Now, when I do that, I flip this the first thing. The next thing I'm going to do is this. I'm going to go ahead and show you how to get I1 without even worrying about the current and stuff like that, the current ratio and stuff like this. Only thing I'm going to do here is say, now, please make sure you see this too. Remember what I've been saying. This side has more turns, right? This side will have a higher voltage. Got it? This side will have a higher impedance. Does everybody understand that, class? Are you with me? So the impedance over there is what? On the actual secondary. Class? 2 minus J1, right? when the impedance comes to the primary, it's going to be multiplied by the turns ratio squared, or multiplied by 2 squared. Do y'all see it? More turns here. When I reflect the load, it goes up by the turns squared. You follow me, class? How many do? You only see your hands. Right? Are you with me on this one? Isabel? You remember how I said that when you reflect things, normally I said that if I looked at V1 here, this way, work with me and you'll see it. V1 is equal to what? Well, V1 would be equal to 2 times V2. Do y'all see that, class? So it's 2 times V2. Now what about I1? Well, I1, more turns, less current. I1 is going to be equal to I2 over 2. Got it? Can y'all see this? Everybody got that? Now, take a look at this. When I take V1 over I1, I get Z1. That would be the Z of the primary is V1 over I1. Well, what is that? That's 2, right? V2 over I2 times 2. Or it's 2 squared V2 over I2. Isn't it, class? What is V2 over I2? Well, V2 divided by I2 is the second impedance. I'm trying to make sure I show you this. So, yes.
Well, for this ratio, it's for V1, it's V1 over V2 over N1 over N2. So what would be 2?
Well, look. V1, right?
Yeah,
Proportional to N1, right?
Yeah, N1.
2.
Yeah, so it's oh, I'm sorry, yeah.
If it was 1 to 2, yes. By the way, I did this problem yesterday for a student of my office, and for some odd reason I put 1 to 2. I'm used to always seeing 1 on the primary side. It was one of these knee-jerk things, so be aware of that. The 1 is on the secondary, not primary. You all see that, class? Make sure you see it. So now, if you see this, this is really going to be Z primary is 4 times Z load on the secondary. Does that make sense? If I could find it, another marker here. These things are really not spent. I guess it's incumbent upon me to bring new ones.
Why is it squared? So should you rewrite that?
Well, just take a look at this for a second. Just do it yourself. If I take V1 over I1, who asked this one? You did? What is V1? 2V2. Put 2V2 here, right? Divided by I1. What's I1? I2 over 2. So 2V2 over I1 over 2 is 2 squared. All right, so the impedance is always related to the ratio of the terms, squared. It's always going to be squared something. All right, now when you take a look at that, and I draw this back on the primary side, now I can say that I can replace, and I want to be absolutely clear, I can replace this entire coil and everything over there with one single thing, and that's the reflected impedance. The reflected impedance, in this case, is going to be equal to 2 minus J1 times 4, right? And I'm going to put it down there. So it's going to be 4 times 2 minus J1, just so everybody sees where it comes from. And that is simply the 2 squared. Now I put back the 4 plus J6 that was there in the first place, right? And here, then I connect this, so this is 24 at an angle of 60 degrees. And I want to get this current. That's what he calls I1. Now you see the key thing is reflecting the impedance, right? You all with me, class? Right? Yeah, I've got to make sure you were in my office asking. Do you all see that? All right, so what is I1 going to be, class?
1.97.
Let me write it down. I appreciate that, but I want to just write it down. Divided by 4 plus J6 plus, and then it's going to be 8, right? Minus J4. I wrote down everything. You can reduce that. 8 and 4 is 12, right? So this can be reduced to 24 at an angle of 60 degrees, and that's going to be 12, right? And it's going to be plus J2. And now, whoever said that, y'all follow me on this one, class? I'm doing it. I want to make sure I didn't confuse you on this one. Now, what did you get for this?
Oh, 1.97. I think it was
1 point, 97 and an angle of, did you say 50?
Yes, sir. 123.
Could you check for me on that one? Does anybody have a solution to it? Is that right? It is right?
I think.
Could you take a look at the solutions? Wait, I need an absolute confirmation or denial. Is it right or wrong?
Yeah, it's right.
All right, you all see what I did there. The reflected impedance was the key. Got it? Now, in doing this, listen carefully, because this is a question, I didn't address this well. You see that this is the reflected impedance of the transformer. Y'all follow me? It's the secondary reflected to the primary side. Everybody see this? This voltage right here is my V1. You all see that? Class? So how do I get V1? Well, pretty simple. I got the current I1. If I just multiply it by that, I got V1, right? I could have done voltage division too. I could have taken this times that impedance over that impedance plus that impedance, right? Either one will get me. So V1 right here would be what? That would be equal to I1 times, and then it would be 8 minus J4. Can you tell me what that is?
17.6 at angle of 23.9 degrees.
17.6, and then you would say that again, sir?
Angle of 23.9 degrees.
Anybody confirm that? Anybody, you got that? All right, what is the answer, the solution manual say? Can somebody find it? Anybody?
The solution menu?
Yeah, I mean, the ones, solutions I posted.
Yeah, it's the same thing.
Is it the same? Now, you all see what I'm doing here, and I'm trying to make it absolutely clear, there's no mess up. I gotta make sure you see the way, this is how I would do the problem, if it was up to me. I'm not gonna write the crazy equations, I'm gonna, yeah.
Some of the homework problems had a voltage on the secondary side.
We'll do one in a second, but let me just finish this one, make sure it's clear. Got that? Now, if I have, that's V1, what is V2 gonna be? Is this the way he shows V2 in the book, by the way? Like that, doesn't he has it at top? Top's positive, bottom's negative, correct? You all see this? Remember, the dots don't matter as long as you move. If you flip the whole transformer, you could put both dots on top or both dots on the bottom. Doesn't matter. All right. Now, V2 would be what? Just think about this. It goes from more voltage to less, half the voltage of V1, right? So it's just equal to V1 over 2. And what's that going to be? 18, so that'd be 9, what is it, 8.1?
8.8.
Same angle, no change in the angle, which is 23.9 degrees, is that right? 23.9 degrees, and that's volts. Now that's V2, right? Please watch me. You'll notice I haven't messed with the current ratio at all. I could, I chose not to, because I don't want to confuse you with that direction stuff. I mean, it is coming out for that turns ratio. If I have V2, what is the current I2 going to be, just by inspection? V2 is like a source now. Class?
V2
over 2 minus J1. Whoever said that's right. So now I can say that I2, and check the answer on this, is V2 divided by 2 minus J1, and that's going to be what? Since that's V2, just divide that by 2 minus J1. I want to make sure we get every part of this problem. Okay, anyone? Anna, did you have this one? Or not?
I got 3.95 and an angle of 50.5 degrees.
At an angle, so you?
50.5.
Anybody confirm that for, is that what the answer in the book is or not? Class? It is? In the solution there? Now, I messed that angle up because I did the currents in. You remember that? Remember that angle was off by, I don't know, 180 degrees, wasn't it, class? The first time, what I'm trying to tell you is this is the correct way to do it, and I stick with the voltage ratios generally. I can use the current, but remember that current is coming out of that dot. That's the key on this one, for transformers. Now, somebody asked me about a problem with a voltage in the secondary. That was you, right? It was the guy with his phone. Yeah, when he gets off the phone, let me know.
Uh,
Which one?
I don't remember the specific problem it had. wondering how you would handle it.
Oh, we'll do one. That's the best way to handle it. Show an example. And really, the key is just the equation, honestly. So for this one, doesn't matter if the voltage on primary, secondary. Let me find one. Is there one?
Yeah, it's just like,
Oh.
you know, these two equations, V1,
Well,
V2.
unfortunately, one of the voltage on the secondary is a coupled circuit, not a transformer, whoever has that. What I'm looking at is actually, I'm looking at 613, but that's a coupled circuit, it's not a transformer. We could make it better.
Did you just say maybe it's an eagle?
Pardon me?
623. I heard maybe it's an eagle.
We can do 623, but it's not a voltage on the secondary. Who said this? Who said 623?
But I just heard it. I don't know why.
I can come up with a problem, how's that?
Yes, yes.
All right, I'll create a problem that is a possible question. Not a very good one, but a possible one. Suppose I have a transformer. First I'm gonna say this is my transformer. All right, dots both on the same side. All right, like this. This is gonna be my V1. This is my V2. All right. Now what I'm gonna do is this. I'm gonna go through this one, and I'm not on purpose gonna mess with the currents right now. I can, but I don't need to. And now I'm gonna put a voltage out here. Let me put a resistance here, just make this 10 ohms. Then put a voltage here, and let's make it easy. Plus to minus, say, 20 volts at an angle of 30 degrees. All right, just make it easy. Now on the primary side, I'm gonna go ahead and say on this side, what I'm gonna have is this. 10 and then J10. And then I'm gonna have a ratio of say 2 to 1. Now some of you figured this out by now. I've got the turns ratio, I've got the dots on the terminals, I've labeled V1 and V2. I can label this as I1 if I want, but I don't need to, right? I don't have to do it. Now, I know that V1 over V2 is proportional to N1 or 2 over N2 or 1. I know that, right? Now what I do is analyze this system as if this was the primary side and that was the secondary. And this should be pretty evident to you. It's the same exact analysis, only we're doing it looking as the secondary like we would the primary. You are with me? Now take a look. What we're going to do for this one is first take a look at the impedance in the secondary circuit. So the load impedance in this case is on the primary, but it's load. That's 10 plus J10, right? Correct, class? Then we go from more to less, means the impedance goes down, right? It goes from more to less impedance by the square of that, or by 4. So that means Z on what I call the primary, it's really secondary, but now on the reflected side would be 10 plus J10 over 4. Do you all follow me on this? I'm reflecting the impedance to the secondary, because the circuit's load is on the primary side here. Y'all with me? It's really just turning the problem around. That's all we're doing. Does this make sense to everybody? I'm doing my best. I'm trying not to make it too crazy. So now what does it look like? It looks like this second coil here is going to be replaced by that. And I want to leave it as 10 plus J10 divided by 4 for a reason. So everybody sees where that comes from. And then I put on the 10 ohms here. And now I've got my voltage here, plus to minus 20 volts at an angle of 30 degrees. Now that's just the secondary side, but that's where the source is, right, class? Got this? You may not like it, but really it's the same exact problems we've been doing, we've just turned them around. That's all we did. Agreed, everyone? Follow me on this. What is this current gonna be right here? I better call that I2 actually. Why don't we call that I2? Well, what is I2 gonna be, class? Just look. It's that voltage, 20 at 30 degrees, right? Divided by, and it would be divided by 10 plus, and it's just gonna be 2.5 plus J 2.5. So that's gonna be the current I2. Do y'all agree with this, class? Y'all see this? This isn't hard, I'm just making sure that there's nobody doesn't understand this, right? You agree? We can get a value for this in a second. Now, what is V2 gonna be, right here? What is V2? Well, V2 is right here, isn't it? Class? So what's V, yeah.
If you rewrite the denominator clear?
Yeah, I can. That is just that impedance 10 plus, and I'll write it as 10 plus J10 divided by 4. It's simply this number here. Whoever, you with me? It's this number. Well, I'm just showing you where it came from. It comes down to 2.5 plus J 2.5. Now, that's going to be that current, you all agree? What is V2 going to be?
I2 times the.
Yeah. V2 is going to be I2 times 10 plus J10 over 4, or 2.5 plus J 2.5. Now, if you want to, you can give me this value. You've got it. Give me a polar. Somebody can crank the numbers for me. I'm really doing my best here to try to make sure this is clear. A problem like this could come up, but it's exactly the same as the ones we've been doing, only now our secondary looks really like our primary. That's it. We just flipped the problem, spun it around. What'd you get?
1.57 angle of 18.69.
At an angle of 18 point what?
69.
Degrees. All right, that would be in amps. That's I2, right? What do you get for V2? $64 degrees about?
I got 5.55 at an angle of 63.7.
5.55?
Yeah, at an angle of 63 degrees.
About 63 degrees sounds right. That's V2 in volts, right? Now, if that's V2, well, I really should say it's V1. I'm so sorry. No, it is V2, pardon me. That's this voltage right here. My bad. Yeah.
Just for clarification, so your N value is, so your N value is N2 or N1?
Well, that's what the book says, but this is the way I'm trying to make sure people see. More turns, more voltage, right? It's always proportional to this ratio of the turns on this side to that side. The one with more turns has more voltage, right? Has less current, has more impedance. I hope I'm getting through to you, all right? So the turns ratio here, technically, if we went from primary to secondary, right? Then it would be equal to 1/2 or 1/2. But this is going to confuse you. Just look at the ratio. If I go from less to more voltage on this side, more impedance.
So it's split, which has the voltages.
Because I get the voltage on the secondary. That's what I'm trying to say. Everything is the same exact principle, it's just, you're taking the primary and whipping it onto the secondary. Take the standard problem and then take the page and flip it. That's what we've done. All right, that's the current I2, that's V2. What is V1 gonna be, class? Just look at it. V2 to V1, it does what? Doubles, yeah, it goes up by a factor of 2. So you just take this voltage and multiply it by 2, right? And what is that going to be? That's 5.5 times 2 is going to be 11 point something, right? Class? Still at 63 degrees. Agreed, class? Everybody? You just double it. Now, if that's the voltage here, V1, then what is the current here? And I'll just call it I1. Class? Just V1, right, divided by 10 plus J10. Can you give me that? I made this problem up, but it's really showing you all aspects of this. Anybody? Class? If I've got this voltage, don't I have this current necessarily, class? Sure. What is this? Well, that's V1. I call it 11.1. And at 63, if you take that and divide it by 10 plus J10, what do you get? 1 point something? An angle of, I don't know. Anybody?
0.785. An angle of 18.
Anybody confirm that?
Yep.
All right. So that shows you, and that's actually a pretty good problem. I haven't thought about doing that way, but usually the voltage is in the primary, the load is in the secondary. Almost always. The things you're going to be faced with will have that in the real world. The loads and yes, sir.
I guess my question was actually, can you have a voltage on both sides
Yeah,
like
you
we
can.
do with the?
Yeah, we could, and then we write two equations. We'd have loop equations.
That's what I was trying to get at.
Because now you can't reflect impedance. You'd have two equations. I'm not going to do that.
Right.
All right, if you want me to, I will.
No.
Oh, please, yeah, do it. Put 3 voltages.
No.
Now, real transformers, I want to tell you, they won't have just one secondary. There'll be 3 or 4 coils off the secondary where they're pulling things, and the sum of the power going out is equal to the power coming in. Those are more involved. That's an electrical engineering problem, not for people that aren't electrical engineers. But you should be aware that in the real world, if you see several actual windings in the secondary with voltages, that's common, very common. Usually what they do, if you have, trying to give you some perspective, if you are a guy and you've got a power plant, or say you've got a plant and you need 480 volts, you need 240 volts, you need 110 volts, and they're coming off 7,200 volts, all right? So I got 7,200 volts on one side. And then I got an iron core. What a transformer really looks like, this is for perspective. You got a solid iron core when they build these things like this. And what they're going to do is wrap, with a whole lot of turns, a primary coil there. Now, all the magnetic flux, if you remember physics, is going to be located with that. It's a laminated iron core. Laminations they stop losses with something called eddy currents. That's beyond the scope of this course, but just appreciate that. Now, I need 240 volts. So now I take a winding, and if there were N turns here, and this is 7,200, then they're going to be less by the ratio of whatever, say 480 by 7,200. If there were N turns here, there's going to be a ratio less on turns here. And then I'm going to have one set of coils here. And that's not this showing the perspective, but now this is going to be plus or minus 480. Then I'll have another set here, less turns yet, and coming off, and I'll have plus or minus 240, and then another set here, plus to minus 120, or as many voltages. That's common. Then what's typically done a lot of times, they're going to take this, we're not there yet, and they put it through something called a rectifier that'll take that AC signal and turn it into DC. And then they'll use that DC signal for their machines, usually. If you guys are working in industry, the IEs especially, you may run into this. You're going to have to at least appreciate how this is done. 7,200 volts is the high voltage line that's running down the street that nobody can get at. Then they have the transformer on the pole that comes off. Those are usually plus or minus 120 to their house. If it's going to an industry, to some kind of a non-residential area, commercial area, then they'll have that inside the actual commercial residence, and it may pull off a whole bunch of different voltages because a lot of equipment runs after 480. And anybody ever work in a plant? Anybody here? All right. Now, if you worked in a mill, typically they're going to have higher voltages than that even. But 480 is a typical one you're going to see. running in a mill, and then you get plus or minus 120 for some of the lower things, and you'll get a live 240 line, 240, but I'm not absolutely sure of that. And those are things that are gonna be used for machinery, heavy machinery. But I'm just telling you to be aware, you're gonna see it, yeah.
The book gives a lot of problems where it's got like weird currents coming in and stuff. Should we just change that all to like the standard that we use? Like currents going out of one dot or into the other? Should we just change it back?
I tell people everything, this, when you're doing mutual coupling circuits, all right? Current always into the dots, I1, I2, voltage always positive at the dots. When you're doing transformers, on the primary side, currents into the dot, on the secondary side, currents out of the dot. But V1, V2 are the same as for mutual, all right? Now the beautiful thing about focusing on the voltage, you'll never mess up the currents because it's reflected impedance that gets it on the primary. Then once you get that primary voltage, the voltage in the secondary is either stepped up or stepped down by the turns ratio. Then you configure the current in the secondary without any kind of mess ups. You get directional mess ups. All right, now we're basically done with transformers. So next, we're not going to do passive filters. The next thing we're going to do, and this is important to a lot of you, and I'm doing it this way for a reason too, are going to be operational amplifiers. How many have heard the term operational amplifier, op-amps? How many are enemies here? Show of hands. You guys use these all the time. You use them primarily for sensors. You take a measurement from a sensor that's in the form of voltage and you amplify it with an operational amplifier. It's very easy to do. Now, if you pay attention to this, I'm going to show you all the secrets about how to do these. These are ideal op-amps and they're going to be as easy as possible. I mean this. So please just bear with me and watch. So this is operational amplifiers, or op-amps for short. Operational amplifiers are something that has thousands, tens of thousands of transistors, and we never ever talk about the circuit that guides these things and really controls them. What we show you is this. We show you a little triangle. This is an amplifying triangle of sorts. It has a negative terminal here, and it has a positive terminal here. These are the input terminals. They're called differential inputs. Then it has an output terminal here. This is V out. What this represents is tens of thousands of transistors possible. Lots of them. You don't have to worry about how this is done. It also has a plus and minus voltage source that is never shown, usually. So, what happens here and what guides this principle is this. There is no voltage difference. So if we take V minus here, V on the minus terminal, minus V on the plus terminal, it's zero. There is no voltage difference between these input terminals. This is going to bother you. Not only that, because of the way of the magic of these electronics, it never allows current in here. So I minus is equal to 0 and I plus is equal to 0, which seems stupid. How can that be? I can take a battery and put it across there and I have a voltage, right? Well, the fact of the matter is if you did that, this operational amplifier would not be working in a linear region. What it does when it works in a linear region is prevents any appreciable voltage difference between these two and no current flows into it. Now, how does that work to amplify things? I'm glad you asked. Watch and you'll see. Now, please watch this. So here, if we make one of these, make that negative positive, now just watch. I'm going to go ahead and put just a resistor R1 there. And I'm going to ground this terminal. And then I'm going to put my voltage source here. Please watch this. I'm going to do this as simply as possible. And I'm going to ground this. I like the ground so I don't have to run wires everywhere. Now I'm going to take a second resistor. And I'm going to say this V out plus to minus with respect to ground. I want to figure out what V out is, and I'm going to show you how to do this. If you remember the rules, no current into either of those input terminals, no voltage across them. Did you hear me? Now here's how it works. If there's no voltage across it, well, what is the assumed voltage at ground? 0. So that's 0 volts, right? Do you agree there's 0 volts in the positive terminal? You all see this, class? What's the voltage on the negative? 0 as well. So 0 volts there. Got me? Or it's like a ground, isn't it, class? But you can't put a ground there, or this whole thing falls apart. There's actually very small voltage there, but it's not even anything appreciable. Now, how much current flows this way? It's just Vs over R1, isn't it? Isn't it? Just voltage divided by R1, because this is grounded, that is, right? How many see this? Are you with me? Can you all see it in the back? Can you see it? Far back. Guys, I don't know how you see anything back there. Can you really see it? All right. So if that's I1, now how much of that current goes into this terminal? I told you it was 0, right? None, right? Where does it have to go? It goes this way. Are you seeing this? I'm doing it this simple because if you see the simplicity, you won't mess up. It's when you start memorizing all these formulas that are out there, you'll blow these things every time. There's cajillions of formulas for operational amplifiers, depending on the configuration. You do the analysis this way, you never mess up. Do you all see what I'm doing? Now, with that in mind, what is the voltage plus to minus here, V2? I1 times R2, right? Y'all agree with that? Not done yet. Well, what's I1? Right? Vs over R1. So I can say this voltage, and you'll notice I've got a plus to a minus, is really going to be Vs times R2 over R1. Do y'all agree with me? Not done yet. Y'all see it here? Right? Isabel, can you see it?
Yep.
In the far back. Okay. Now, what is the voltage here? Now, this is where people mess up. So watch. If I want the voltage here, y'all see I can start at this negative terminal, right? I always say start at the negative terminal, the voltage you want, work around. I got 0 volts here, 0 volts here, agree? But this is a voltage drop, right? It's minus that voltage before I get to the plus terminal there. Do y'all see that? So that means V out is equal to minus Vs times R2 over R1, or we call this the amplification factor of the voltage, or AV, is equal to V out over Vs, and here it's minus R2 over R1. Now, hear me now. Remember, these are AC signals that are going to be into that. Typically, it's a time-varying signal that goes in between the plus and minus, for Vs would be plus to minus some voltage. Are you with me? It's something that's time-varying. When I look at this, I notice I can control the magnitude of the output by getting the ratio of R2 to R1. Do you all see this, class? If I wanted 1,000 volts more than my input, I'd make R2 1,000 times greater than R1. Now, the negative sign means it's inverted. It means that the signal on Vs is going up, right? I mean, it's going to have a positive value. The output would have a negative value, but would be scaled by the ratio of R2 to R1. This is the simplest possible operational amplifier circuit, but it's the one that's used most commonly right there. How many have run into a circuit like this? If you've done sensors, you have to have run into this one, because this is used everywhere. I guess the word ubiquitously is what you hear all the time. It just means you can't get away from it, right? If you do sensors, anytime you build a sensor. MEs and aerospace engineers probably going to run into this all the time. And it's cheap to make it, which is nice. This is ideal. Now listen, what if instead of that was with a resistor? What if we talk about something a little more all-inclusive? Make it impedance. So if we make this Z2, and make this Z1, just put a block there, I don't care what they are. Now, what I can get is this. Well, still I1 here is going to be, I1 would be Vs over Z1, right? And still, this voltage right here, V2, would be I2 times Z2, or it's really going to be Vs times the ratio of Z2 over Z1. You all agree with me? I'm just changing R to Z, right? And then my output voltage, instead of being a ratio of resistances, it's a ratio of impedances. Do you all see this? So now I can come here and I can say that now my V out is just going to be Z2 over Z1. And this is the most common. Then they'll have the amplification factor for op amps, voltage amplification, as simply minus equal to V out over Vs and be equal to minus Z2 over Z1. I have one last thing to say. Are you with me, class? This is very, very common. Now, the final thing I want to say is, I'm going to give you some operational amplifier problems to do. But what I'd like you to do when you're doing them is remember the law. No current into the differential terminals. So you're always trying to get the voltage at one of these two terminals. That's the bottom line. Usually a good starting point. Sometimes you can't. And then since no current goes into them, you know whatever voltage is on one side that causes a current, that current will always be shunted around it. Follow me, class? I'm going to give you some of them. So the next question is there a quiz on Friday? I would prefer not. I'd like to turn it to a Monday quiz unless somebody objects because we're just starting, yeah?
Is there any possible way to make it like an attendance quiz?
No. If this class is monitored, if I start that stuff, I'll get fired. They don't allow you to do cheap stuff here. This is a monitored class.
What if you ask things that, technically get wrong, like how to.
Oh, don't start. Don't. I mean, if you want to be a lawyer someday, be a lawyer, but not here. No, we'll have it set. I'd like to do this. I'd like to put the quiz on this material Monday so I have time to flesh it out on Friday. All right? And this is not bad, but it requires you to think hard. Yeah.
I do want to go ahead and ask when the test is planned for.
We're going to vote on the test on Friday. Be here if you want to vote. Then I'll get it.